And what's the charge?
-1.
Yeah, 1 negative. So aluminum is Al3 plus, right? Acetate is C2H3O2. So how do I make a compound out of that? Al parentheses
C2H3O2.
Okay.
Parentheses
3. Okay, good. And it says it was aqueous. I'm going to put AQ. Okay. Potassium sulfide. What's potassium's charge?
+1.
Plus. What's sulfide?
Negative.
So what is sulfide though? S. So it's I all by itself and 2 minus, right? Okay, so how do you make that a neutral compound? K2. I heard somebody say K2 what? S. That's aqueous. Okay, that's the first part. This was 2 chapters ago and a test ago. It should be rolling off the tongue by now. So now we're going to swap the anions. We're going to take these suckers. We're going to swap them out, right? We're going to swap the acetate with sulfide. So I'm going to put aluminum with sulfide and potassium with acetate and make new products. So try that out if you haven't yet. So what would aluminum and sulfide make? What would potassium and acetate make? Figure out those.
Do you want us to balance the equation?
Yeah, we'll do that too. But yeah, that's fine. Yeah, that's fine. You can do it now. But for now, at least just get me the products with the correct ratios, and then we'll do the solubility rules, and then we'll balance it too. Okay, so here's the charges already, right? Aluminum 3 plus and sulfide 2 minus. How do you put that together? Al2S3. And then, I don't have room to put it down here. And then potassium K plus with acetate negative. How does that combine? Right, just one of each. KC2H3O2. Good. Okay. Okay, you're awfully quiet and looking confused. What can I do to help? You're just swapping them, right? You're just new partners. So now put aluminum with sulfide. Now put potassium with acetate.
So when we swap them, we balance them again based on their charges?
Yep, exactly. The wrong way to do it is say, oh, it was K2 here. I'll just put K2 here. It was 3 acetates. I'll put 3 acetates. Nope, you can't do that. You just balance them always based on charges. Okay, next let's do. Okay, well actually next I do one of 2 things. You can either balance the equation next, or you can do solubility rules to figure out if they're solid or aqueous next. Let's just balance it next. So obviously it's not balanced right now. So how do I need to balance that? What coefficients do I need to put in here to make this work out? So balance your aluminums, balance your acetates, balance your potassiums, balance your sulfides. What do you think? Anybody? How many aluminum acetates do you need? 2. Okay, good. How many potassium sulfides do you need?
3.
How many aluminum sulfides?
1.
Just 1, okay. How many potassium acetates?
6.
Okay, now you balanced it good, right. Okay, now let's put in our phases, or our states. Aluminum sulfide, is that solid, which means insoluble, or is that aqueous, soluble? So I told you Monday to run those 5 little solubility rules. So what's the rule for that? Is there a rule for that? Remember our rule was if it's a group 1 element, like lithium, sodium, potassium, they're always soluble. If it's ammonium, it's always soluble. If it's nitrates or acetates, it's always soluble. Remember those rules? If it's chloride, bromide, iodide, it's always soluble, except with silver, lead 2, and mercury 1. If it's sulfate, it's always soluble, except with barium, lead 2, calcium, and strontium, I think. Everything else is insoluble. So where does that fall into those rules? It's not any of those, right? So it's going to be what? AQ or S? It's going to be a big solid, going to be a big brick in the bottom, yes. How about potassium and acetate? It's going to be soluble. Because, why? Yes. Actually, there's two reasons. All potassiums are soluble, no exceptions. All acetates are soluble, no exceptions. So definitely, so I'm going to put AQ. Probably can't squeeze it in after, so I'm going to put it here, kind of. But it should typically go right after that. So, okay. Okay, let's try another one here. Okay, aqueous barium chloride is added to a sodium carbonate solution. Aqueous barium chloride. So, what's barium chloride's formula? Ba what? BaCl2. Barium's 2 plus. Chloride's 1 minus, so I need 2 chlorides. And it says it's aqueous. It already tells you that, so I'm going to put AQ. But if not, you would know that because all chlorides are soluble, except silver, lead, and mercury. That's not silver, lead, or mercury. Plus sodium with carbonate. So you know sodium's charge. Hopefully you know carbonate is. Put them together. What do you get? Close. What's the charge on sodium? What's the charge on sodium?
1.
Sodium's in group 1. It's 1 plus. What's the charge on carbonate? 2 negative. So how do I put them together? Na2, 3. And is that solid or aqueous? Yes. Well, yes. Again, it tells you solution, but even if not, you know anything with sodium is aqueous. Okay, good. So let's swap partners. So what will my first new compound be made of?
Barium.
Barium with what? With carbonate. Okay, so what's barium carbonate? Just naming. What's barium carbonate? So what is it? BaCO3. Okay. What's going on there? Okay, is that going to be solid or aqueous?
Solid.
Solid, because it's not one of those rules. Okay. Plus, what else am I making?
Salt.
Yes. What is it?
Sodium chloride.
Sodium and chloride. Okay, what's the formula of sodium and chloride? Okay, just NaCl. So again, I'm going to show you the number of mistakes students make is they just keep those coefficients. They say, oh, it's Na2 and Cl2. I'll just put Na2Cl2. You can't do that, right? You can't do it that way. You got to say, oh, sodium's plus, chloride's minus, so just one of each. Okay, is that solid or aqueous? Is anything with sodium always aqueous? Now let's balance it. How would I balance it?
2 in front of the NaCl.
Yeah. 2 chlorides on the left, so I need 2 on the right. 2 sodiums on the left, so I need 2 on the right. Okay. Okay, your turn. Try this one. Lithium phosphate and potassium sulfate. Try it out. Yeah, Michael. This is a polyatomic. This is
Computer's correct. What? Make looking at yours goes with some potassium.
CO3 is so now it's CO3 with barium. Chlorides. So that's not right back here. So yeah, barium 2 plus.
Phosphate has a
Chloride is up there. Minus. Sodium is up there. Carbonate is up there. So this is a unit cell. I need 2 of these sodiums to balance it out. So now I'm just taking this barium 2 plus with this carbonate 2 minus. So that is what we just put together. Does that kind of make sense?
Yeah.
And these just go together.
Sulfate is SO4. Heavy sulfide. S would be for sulfide. Sulfate is SO4. 2 minus.
Okay, help each other out. If you haven't yet, what's lithium phosphate? Ask your neighbor. What's potassium sulfate? Check with your neighbor. Make sure he's got the reactants right. And then change partners. And then balance. Do your states. Okay, compare, help each other out, let's see what you're doing. See what your neighbor's doing.
No. Remember like 2 classes ago when I just said I don't know why. It's bad. When it was a lot, it should be more.
Okay, let's go over it. So, what is lithium phosphate's formula? What's lithium phosphate's formula? Li 3 PO4, and that is aqueous or solid? I told you, but if not, you would know that. Why?
Group 1.
Lithium. Anything with group 1 with the lithium is aqueous. So let me show you. The aqueous goes right after it. Okay. Do not write it up here or down here or weird places. People who don't. Just goes right after it. Okay. It's like 4 aqueous. Okay. Okay. What is potassium with sulfate? Somebody else. K2SO4. Good. Okay. And it tells you it's a solution, but if not, you would know it was aqueous. Why? Potassium. Anything that has potassium, right, is... Okay, good. Now we're going to swap partners. So I'm going to swap phosphate with sulfate. So I'm going to make lithium sulfate and potassium phosphate. So what's lithium sulfate? Aqueous or solid? Aqueous. Why? Convince me. Lithium. Anything with group 1 or lithium, right? Has to be soluble. Plus, what else do I make? K3PO4, potassium phosphate. Aqueous or solid? And again, why? Potassium's in group 1. Has to be soluble. Okay. Everything's aqueous. What's that mean?
No reaction occurred.
No reaction. Now, you could go ahead and balance it, but we don't even need to because really nothing actually happened. So all that happened was lithium and phosphate dissolved and is swimming around there. Potassium and sulfate are swimming around there. And at the end, they're all still swimming around. Nothing combined to make a solid or a gas. So literally nothing happened. So yeah, you can just write no reaction. Yeah. But I guess if you wanted to balance it, you could go 2, 3, 3, 2, or something like that if you wanted to balance it. But no reaction, so just no reaction. Okay, so practice that. On the homework, you can practice some of those. So now what I just wrote was called the full chemical equation. Oftentimes called as well the molecular equation because it shows everything, every molecule it shows in there, okay? So that shows all the reactants, all the products. But what I want to show you now is what's called the complete ionic or the total ionic. And that shows really how is this, what's really going on in that beaker. So it takes anything that's aqueous, which means it has broken apart into ions, and it just shows the ions. See how it's showing the ions? But that's a solid, so that is not ions. That is really, so that stays the same. But the ones that are aqueous, we're going to break them up and show the ions. So that's why it's called the ionic equation, because it shows the ions. So just how's that work? Anything aqueous, break it apart and clearly show the ions. How many ions? What are the ions? Etc. If it's not, if it's a solid, a liquid, or a gas, just keep it the same. So solid just comes right down. Okay? Okay, then there's a third one that just tries to get to the meat of the reaction, called the net ionic. But I'm pausing because I see like he's still writing. Okay, so you have the full equation, or the molecular. You have the ionic, right? Okay, now let's go to the next one. That's called the net ionic. Now some of you started writing again. I thought you were done. Okay, so now we're going to look for what are called spectator ions first. So spectator ions are, so here it is again, here's the same equation I just had. This is the complete ionic equation. Which ions appear on both sides? Which ions do you notice are on both sides? They're not doing anything, they're just spectators. They're just kind of watching the reaction go. I see potassium, K plus on both sides. What else do you see on both sides? I see nitrate on both sides. So those ions, they aren't really doing anything. They're just kind of there watching the show. So I'm going to cross those out. And then whatever is left, that's called my net ionic. That's the net. So the first one was, with the gross kind of. Then I get rid of that and you have the net. So this really shows the meat. This really shows what really happened in that beaker. Oh, a silver and a chloride combined to make silver chloride. Potassium and the nitrate were just like, again, they're just spectators going, yay, good job, silver chloride. Make it happen. They weren't actually doing anything. They're just kind of there for moral support. They are the bench warmers. Okay? So that's all you do. So you have the full equation, break apart the aqueous ones, cancel out whatever you see on both sides, then write whatever's left. And that's called the net ionic. So let's just try a couple of those. Everybody have that written down that wants it? Scream now, forever hold your peace. No one's screaming. I'm advancing the slide. Okay, let's try one. So we're going to do the same thing we just did. We're going to write the full equation first. Then we'll do the next step. So first, the same thing. So what's iron 3 bromide? What's potassium phosphate? Swap the anions. So let's do that. So what's iron 3 bromide going to be? What's the formula for iron 3 with bromide? FeBr3. Fe3 is 3 plus. Bromide, find bromide, it's 1 away, so it's 1 negative. So FeBr3. What's the state? Aqueous or solid? I heard both. Convince me why it's aqueous or solid. What's the rule you're using to base that off of? Bromide, yeah. Bromide's always soluble, except with silver, lead 2, and mercury. And that's not silver, lead 2, or mercury, so it's soluble, aqueous. Potassium with phosphate. So what's potassium charge? What's phosphate charge? Put them together, what do you get? K3PO4. Aqueous or solid? Why? Potassium. Yes. Okay. Let's swap them. Now let's swap the bromide and the phosphate. Let's make iron 3 phosphate, right? And potassium bromide. So what's iron 3 phosphate's formula? FePO4, because it's 3 plus and 3 negative. Good. Solid or aqueous? Solid. It's not one of those rules. There's no rule for iron or phosphate, so it's a solid. And then potassium with bromide. KBr, right, good. Aqueous or solid? Aqueous because of potassium. Okay, good. Let's balance it. How do you balance it?
3 and for the KBR.
3 KBr right there. Good. Okay, so that's the molecular molecular equation, or the full equation. Okay. So now we're going to write what's this called, the ionic equation. So what I do for that is anything there that was aqueous, it really has dissolved into ions. So I'm going to write, okay, what ions would FeBr3 dissociate into? So what ions would that make?
Fe3 plus aqueous.
Okay, it would make an Fe3 plus, right? Aqueous. What else would it make? How many Br minuses though?
3.
Br3, right? So it's going to make, plus is going to make 3 Br minuses. Let me just show you that very clearly, right? So 3, right? So there's the 3 bromides, there's the iron. Okay? What does the K3PO4 dissociate into? What is it? Take a guess. You can be wrong, it's okay. It's going to make 3 potassiums, right? Because there's 3 potassiums with the phosphate, so I'm going to write 3 potassiums. 3 potassiums, aqueous. And then, what else? PO4, which is what? What's the 3 negative? Okay. Okay. What do I do with FePO4 solid? What'd you say? Nothing, right? Yeah, it's a solid. So solids you don't do anything with. So just write it again. FePO4 solid. Okay. Oh, I have another aqueous. I have 3 potassium bromides that are aqueous. So what ions will 3 potassium bromides turn into? It's going to make 3 potassiums, aqueous, and 3 bromides. You see that? 3 potassiums and 3 bromides, right? I can't tell if you get that or not. Are you getting that? You see why it was 3 potassiums, right? And now it's 3 potassiums and 3 bromides. Okay, so that's the complete ionic equation. Now we're going to say, okay, so that equation is basically, it's everything in the beaker at this point. Right, because there's irons floating around and bromides and whatever, right? And then they react and they make this. But which of these are the spectator ions? Let's go through and cross out the spectator ions. Which ions do you see on both sides?
Iron.
Nope, there's not iron on both sides. Bromides on both sides. I see bromides on both sides. I see potassiums. And you should always see the exact same number. If not, then you didn't balance something right? If it's ever like 3K and 1K or 2K, oh, must have had a mistake, because they should always be the same if they're balancing. So make sure they're the same. Okay, so now we just write whatever's left as the net ionic. So what's left? Iron 3 plus, right? Aqueous. Reacts with phosphate, good. PO4 3 minus, aqueous. To make FePO4 solid. So there you go. So that's the last blank. That's the net ionic you made. Yeah, so that's what really is going on. The iron and the phosphate are actually combining. The bromide and the potassium are just kind of there for moral support. They're just there to help the iron and the potassium get in the fight. They're just bringing them along. Okay? Let's do one more. try this one. Ammonium carbonate and copper 1 sulfate. So first write your molecular, change your partners, and then break up the aqueous, cancel out the spectators. Let's go to those 3 steps. Help each other out. Raise your hand, ask me questions. Happy to help.
Copper and C. First, the letter for copper is C.
Oh, yeah.
Yep.
Okay, so compare with your neighbor first. What's ammonium carbonate's formula? What's copper 1 sulfate? Make sure you're on the right track. Check yourself
Show me also for the
before you. What do you get for ammonium carbonate? What do you get for copper 1 sulfate?
reactants.
Solid, yeah.
What's the second one, Chris? I think that's solid.
Make sure. Make sure.
Oh, I didn't see that.
Yeah. So there's no reaction?
Right? So it's 20.
Why is there no reaction? They're all aqueous?
Just kidding. They're not. I don't know. I feel like it's gonna be.
What's the rule for sulfates?
It's for
It's
barium,
except for
lead,
too.
strontium, and
This is
calcium.
lead one.
This is what?
Lead one. Oh my god, that was copper one. Yeah, I don't have
Yeah.
copper on here. I have calcium.
Yeah. Okay.
Yeah, it's for calcium, barium, lead, and strontium.
Okay. Okay. What is this? Ammonium copper?
It should be that one and that one and that one and that
I
one.
was just kidding.
The positives go with the negatives. These are both positive. These are both negative.
So for the ammonium sulfate, there's still no.
Okay, so ammonium sulfate.
It doesn't fit into the exceptions. Unless there are more that you didn't show us.
No, I'm just looking there. So ammonium sulfate. And then what did you get? Copper. What's
carbonate.
copper?
Cu.
Oh. Oh my gosh.
Okay, so what's the rule for carbonate? What's the rule for carbonate? Yeah.
No, the copper is a solid because there's no more carbonate. Yeah. The reason why you didn't write it is because there isn't, so it's gonna be solid.
Oh my god,
Duh.
Right.
Yeah, I messed up too.
Okay. we're going to have ammonium with carbonate. What's the formula for ammonium carbonate? Parentheses. NH4.
Parentheses 2.
Okay.
CO.
Okay. Aqueous or solid?
Aqueous.
Okay. All ammoniums are aqueous. Copper 1 with sulfate. Cu2SO4. Solid or aqueous? Aqueous.
I'm confused on that
Okay, why?
one. Okay. Because I know
On the solubility rule or on the formula?
putting it like that.
Okay, so copper 1 is 1 plus. That's copper 1.
I thought 1 meant that we only used 1 copper.
No, 1 means the charge.
1 means it's charge. Okay.
It's the last one was iron 3. We didn't use 3 irons. We used 1 iron because it was 3 plus. The previous one we did was iron 3 bromide. It was FeBr3. It was just 3 plus. Yeah, yep.
So we're using copper.
Roman numeral is the charge, not the number of the copies.
Okay.
Okay, so now let's take ammonium and make it with what? Ammonium what?
Sulfate.
Ammonium sulfate. So what's ammonium sulfate's formula?
SO4.
Oh, ammonium sulfate.
Sorry.
Parenthesis NH4, parenthesis 2 SO4, aqueous, yes. And I'm just swapping these, right? Now I'm making copper 1 with carbonate. What's copper 1 with carbonate?
Cu2.
Cu2CO3. Solid or aqueous?
Solid.
Solid. There's no rule for carbonates or coppers, so it must be one of the solids. And it looks like it's already balanced. So that's convenient. Okay, now I want to find the complete ionic equation. So what do I do?
Okay, all of it increases.
You cancel out what you see on both sides.
Not yet.
Oh, no,
No, that's the next thing. First, yes. Hold on. Yeah. So whatever is aqueous, break it apart and show the ions individually there. So ammonium carbonate. What ions will that break up into?
Ammonium.
How many ammoniums?
2.
2, right? See the 2 there? See this 2? 2 ammoniums. Put in the charges because it's an ion. And what else?
CO3 2 minus.
CO3 2 minus. Put in the charges. They're ions. All right. So you see that? All right. So this makes ammonium and carbonate, right? Okay. What will the copper 1 sulfate make?
2 coppers.
2 Cu. What's the charge? It's an ion. It's got to have a charge.
Plus 1. 1 copper.
It's copper 1, so 1 plus. That's what's going to get you, I'm afraid. And then what else?
SO4.
Sulfate. And what's the charge?
2 negative.
2 negative. Good. Okay, good. I run out of room, so I'll start writing down here. Okay. Goes to. Okay. What do I do with the ammonium sulfate?
2 ammonium.
Also, there's 2 ammoniums, right? You see that? So 2 ammoniums. Don't forget the plus, because ammonium is NH4 plus. And a sulfate. What's sulfate?
That's still the same. That's personally I would put the copper.
Negative 2.
2 negative. Yeah, not negative 2. 2 negative. Okay. And solid. So what do I do with the solid? Don't split it up. Just leave it together.
2 plus 1 is the same as 1 plus 2.
Okay, right? So any of these, you just dissociate them right into their ions. But you have to put those charges in, right? It's not, copper is not just Cu. It was copper 1, so Cu plus. Sulfate, SO4, 2 negative. Okay, so now what do we do, Nicole?
CO2.
Cancel out.
Cancel out whatever ions are on both sides. So which ions do you see on both sides? I see a sulfate on both sides that goes bye-bye. What else? 2 ammoniums on both sides. Right. Okay. So now I just write whatever was left. So what was left? So I'm left with 2 coppers, and a carbonate going to copper 1 carbonate. And the order doesn't matter. You could have written the carbonate and the coppers. The order doesn't matter. Just as long as whatever's on the left, whatever's on the right is in the right places. Yes, so yes, you could have written CO3 2 negative plus 2 coppers goes to that. That's fine too. It doesn't matter. I just normally put the count on it first, but it doesn't really matter. Okay. So where are you struggling? How can I help?
Do we have to put the charges?
Yes, if it is by itself, it's an ion, it has to have the charge, yeah. Of course, these don't have charges because these have been neutralized to be neutral, but these have to have the charges, yeah, right. Yes, whoever's going to read.
For the test, are we going to have to memorize the solubility chart?
Yes, those 5 I told you.
Okay.
Yep, those 5 rules I gave you on Monday. Yeah.
For gases, you have to split for that.
Gases you don't split, liquids you don't split, solids you don't split. Only aqueous.
Okay.
Only aqueous split apart. Yes.
Can you push the test back to Wednesday?
Like I said, I will see how it goes with our lecture today. If we get through everything today, we'll keep it, but if not, we'll push it back till Wednesday. Okay. So, oh, I'm sorry, I'm going to go back there. So, what else was there confusion on? What else can I help with there? Anybody? What else was there on that? So, you kind of getting it? Not really? Kind of, sort of? You want to try one more? Okay, yeah, go ahead.
So I guess where I'm getting confused with, so when we wrote out like the Cu2 and then the sulfate,
Uh-huh.
how did you find out that the copper was 2? Because technically it says 1, right? So are you taking the 2 from,
How did I find out the copper was 2?
so like
What the rubber
it's
number?
CO42, so you're taking the charge from the sulfate and you're putting that with the copper? Yeah.
So when I was writing the formula, you mean, for this? The very first thing I did?
Figured it out.
You just always base it off the charges, so it was, let me just erase here a little bit. So like ammonium is NH4 plus carbonate CO3 2 negative. So how do I make ammonium carbonate? Oh, I need 2 of the pluses to balance out the 2 negative here.
Okay.
What do I do with the copper 1? Copper 1 plus, sulfate, 2 negative. So same kind of deal. So I got a 1 plus and a 2 negative. So I got to have 2 of the 1 plus to balance out the 2 negative.
Okay, that makes more sense.
Yeah, so just the same thing, yeah, with the naming stuff. Okay. Oops. So, you want to do one more?
Yeah.
Okay, let's do one more. Let's try it out. Calcium sulfide, and tin-4 acetate. So use your naming skills. Try that out. So let's see what we got here for calcium sulfides. I'm going to do it kind of quickly. So CAS, solid or aqueous? Solid. Tin-4 acetate, SN parenthesis C2H3O2 parenthesis 4. All acetates are soluble, so aqueous goes to, we're going to swap sulfide with acetate. We're going to make calcium acetate. So Ca parenthesis C2H3O2 2 aqueous, because all acetates are aqueous. And then tin-4 with sulfide would be SNS2 solid. Is that right? What you got? Now let's balance it. 2 here and 2 here. No? Yes? Maybe? Think about it? Okay, good. Got the thumbs up from Daniel. Feeling good about that. Okay, let's see. So now we take all the ones that are aqueous and break them apart. So what do I do with the two CASs? Leave them alone because it's not aqueous, right? It's solid. So 2 CAS just stays 2 CAS. What do I do with the tin and the acetate? So that's aqueous, so I break it up. So what will it make? Tell me what ions it's making. They better be ions. SN4 plus, aqueous, good, and 4 acetates, 4C2H3O2 negative aqueous, good. Okay, what do I do with the 2 calcium acetate aqueous? So 2 calcium acetates make 2 calcium, right? So what do I write? 2Ca what? 2 plus aqueous, and yeah, there's 2 times 2, so everybody see it's 4 acetates, right? Everybody see why it's 4? Okay. So 4, I'm running out of room here, so I'll go write it down here. 4 acetates, 4C2H3O2 negatives, aqueous. And what do I do with the SNS2? Leave it alone, because it's a solid. So what cancels out? 4 acetates. That's it, right? Everything else stays the same. So now if we just write whatever was left. So let's see. I'm going to write 2 calcium sulfide solid plus SN4 plus aqueous goes to 2 calcium 2 plus aqueous and SNS2 solid. That's what was left, right? Yay! No? Yay. Where am I losing you? You know the big thing that always gets you still? That naming. That's why I told you way back when, that's probably the number one thing you have to know how to do the name, because it comes back and haunts you this chapter and the next chapter, and it keeps haunting you, so you can just say, never mind. Past that, no, we're not. We're going to keep using it. We're going to keep using it. So go back, keep practicing, do the flashcards, watch the videos if you need to, try the naming games online. Just got to know it. Okay, well, let's look at how do I measure the concentration. So if something is aqueous, if it's NaCl aqueous, well, is there a little bit of NaCl in there, or is there a lot of NaCl in there? Well, we can measure what's called the concentration. So in just a general, like a qualitative sense, if you say, oh, it's a dilute solution, it means there's relatively very little of the solute. And if it's not, you would say, oh, it's concentrated acid, or oh, so that means there's relatively a lot of solute. But those are just very, like I said, very qualitative terms. They don't really have a numerical value, So dilute is, like I said, just a very small amount compared to the solvent. Concentrated, a lot of it compared to the solvent. But, of course, it's helpful to put a number on that, right? Well, numerically, what do you mean? I mean, how many grams or how many moles are in that? So we're going to look at a few different ways of measuring that concentration in grams, moles, different things like that. So I'm going to go on. Let's look at, the first one's called mass percent. So mass percent, just what it sounds like. It is the grams of the solute over the total grams of the solution times 100, because it's a percent. So it's how much solute do you have over how much of the total solution. Of course, the total solution is made up of solute and solvent, right? So if I put salt into water, salt is my solute, water is my solvent. The whole solution is the salt and the water, both together. So it's just solute over solution times 100, because again, it's percent, so everything times 100. So for mass percent, you just use the masses. How many grams of sodium chloride do I have? How many grams of water do I have? And then just plug them in there. So this one, you've seen this all the time, all of your life, whether you didn't know it or not. You'll say, it's a 3% hydrogen peroxide solution, or whatever it is, right? I mean, it's percent out of 100. So, but in our case, a percent out of 100 is out of the total solution. So I'm just saying, right? the solution has two components, right? Solute and solvent. You agree with me on that? So when I say solution, I really mean, the solute plus the solvent. That is the same as the solution, right? Okay. So let's just do one real quick. Let's say you go in the lab and you take 5 grams of NaCl, dump it into 97 grams of water. What's the percentage? What's the mass percent of that solution? What percentage of a sodium chloride solution did you just make? Well, we're going to take the mass of the solute. So how do you know which one's the solute? If there's 2 or 3 or 4 things, which one do you pick is the solute versus the solvent? How about that one? Which one's the solvent? Yes, the solvent's the one in the larger amount, right? So obviously in this case, there's a lot more water than sodium chloride, so we would consider water the solvent. So I'm going to take the mass of the solute. So what do I put on top? Which one's the solute? 5.00 grams, right? Over what? 102, right? So the whole thing, not just the water, the whole solution, the solute plus the water, the 5 plus the 97. 5 plus 97. So that, yes, that is 5.00 grams over 102.0 grams. And then it's a percentage, so times 100. Right, you're absolutely right. I got 4.90%. So it's a 4.90% sodium chloride solution you made. So just like any percentage you've been using all your life, way back in grade school, the part over the whole times 100. The part over the whole times 100. Percent of quarters in your pocket. Percent of men in this room. Percent of whatever. The part you're interested in divided by the total over 100. So in our case, it's the part I'm interested in, sodium chloride, over the total times 100. Just like any other percentage. Okay, let's just try one. So it's your turn. What's the mass percent of ammonia if I take 3.9 grams of ammonia and put in 65.0 grams of water? What's my percent ammonia solution? While you're doing that, I'm going to peek ahead here on my PowerPoint. Is that birds chirping? Is that like a phone making a chirping noise? Is it really birds chirping? Did you hear that? No, you didn't hear that chirping noise? Maybe I'm going crazy. Maybe I'm losing my mind here. Very possible. You don't hear that?
Yeah.
Definitely a real bird. Somebody has a bird in their pocket or a phone making bird noise. Okay. It's a very happy bird. Okay, talk it over. You should be done. This should be quick. What'd you get? $5.7%. Anybody else? Nadia's nodding her head. Sydney, give me a thumbs up. Awesome. Okay, so 3.9 grams over the total, which is 68.9 grams, right? Times 100. And I'm sorry, 4.7%. Is that what you said? Man, that is one noisy-ass bird. That's a loud bird. He has some lungs on him. Man. Oh, is that what it is? Mating season. It's like, bring it on, ladies. Okay, so that's mass percent. Okay, I'm going to skip the next one because I think this is pretty straightforward. You can also do it with volume. Same way. The volume of what you're interested in over the total volume times 100. You could do them both in milliliters. You could do them both in liters. Doesn't matter. All that matters is as long as they're the same unit. So I couldn't use 1 in grams, 1 in kilograms, or 1 in milliliters, 1 in liters. As long as the same unit, it doesn't matter. So same thing. The part you're interested in over the total times 100. But now we can do it with volume. So let's say you have a bottle of, I don't know, beer, and it's 8% alcohol. That is probably a volume percent. There's 8 milliliters of alcohol out of every 100 milliliters of the whole solution, the whole beer. Could be mass, but I'm guessing it's probably volume. Okay, but same thing. Part over the whole times 100. Just now we're using volumes. Again, just keep in mind though, gotta have the same unit. Milliliters and milliliters, or liters and liters. You can't take milliliters of the solute and liters of the total. That won't cancel, right? So just make sure they're the same unit. Okay, so let's just do one. What is the volume percent of bromine in a solution prepared by dissolving 12 milliliters of bromine in the solvent carbon tetrachloride, and they're making 250 milliliters of solution? So part over the total times 100. So which one goes on top? 12 milliliters of bromine. What's my total solution? Actually not. Read the question again.
Solvent, so we subtract.
No. Yeah. 250. 250 is the total solution, right? It said they added it until it came to be 250 is the solution, right? Again, it's solute over solution, not solute over solvent, which is what you were thinking, I think there. It's solute over solution, and it is 250 solution. Now, if it said 12 bromine and 250 carbon tetrachloride, then you would add them together to make. But it says it's dissolved in it, and the solution is 250. So 12 or 250 times 100. What is it? What's the percentage? I'm sorry? 4.4%?
4.8.
Sorry, geez. Excuse me. 4.8. Man, I get saucy. Okay, so the solute over the whole solution times 100. Now, one other one you might use is you might compare mass and volume. This is commonly used like an IV solution, like in hospitals. It'll say it's a 5% whatever solution. Oftentimes that is MV. It's the grams of the solute you dissolved in how much total solution. So this one we're going to have to use grams for the solute and milliliters for the solution. So I took 5 grams of salt, I put it in 100 milliliters of water. Voila, I made a 5% sodium chloride solution, MV solution. So we have mass, MM, volume, VV. Now we have mass, volume, M/V. So if it says, oh, it's 5% M/V, it means it was done this way. If it says 5% VV, it means it was done volume. The 5% MM means mass. That's why I've been showing you all those little MVs, MM, VV. Okay. So yeah, 5% mass volume means 5 grams out of 100 milliliters. 5 out of 100 grams per milliliters. Okay, let's just try this one. What's the mass volume percent of a solution? Yes?
Do you think that we could do B for sample 6? Because I looked at it and I don't really understand.
Okay. Wait a minute here. Let's skip it. Come back because I thought yeah, you're right. I know why, but I thought I moved all of those after this. Come back here after this part. Okay, let's just try it. Why not? I'll just do it now. Okay, let's try it. Let's go back and do B first. So, what amount of solute in milliliters do I need to prepare 225 milliliters of a 15% volume isopropyl alcohol solution? So, what does 15% mean? So, okay, so it's 15%, yeah, which means out of, so, okay, volume, what's volume mean? Yeah, so it's comparing like milliliters of solute to milliliters of solvent, right? I mean, solution, right? So 15% is like, oh, well, there's 15 milliliters of, what was it, isopropyl alcohol? I'll just put alcohol here for short. Out of every what? If it's a percentage, out of every 100, right? Of the whole solution. Does that make sense? Because 15% means, 15 out of 100. So how much total solution do I have, though? Now I want to know, well, how much alcohol? Oh, well, there was 15 milliliters of alcohol for every 100 milliliters of solution. So what'd you get? $34? Okay. So that's how much so out of the 225 total, 34 of them is alcohol, and the rest must be water. That's what we're saying.
Can I do 225 times 0.115? 0.15 for me.
Yes.
Still get the same.
Yep, you sure could. You absolutely sure could. Yep. Okay. So now I have some more of those work like that. Yes, that one there was in a weird place. I thought those were all later on. Okay, so mass volume. Now we're going to combine mass and volume. Again, just put your mass in grams, put your volume in milliliters, you'll be fine. So the first one's easy. Just take the mass, 75 grams. I can get my stupid thing to respond here. Over the volume of the whole solution, which was 250 milliliters, times 100. So what is it? How much? 30?
30.
I'll put a little decimal because it's two sig figs. Okay. Okay. Now, how about this one? This is kind of like the one we just worked. It says, how much solute in grams would I need to make 450 milliliters of a 2% mass per volume solution? So this 450 is the what? That's the total solution. All right, that's the total solution. And the 2% MV, so what's another way to think of the 2%? We just kind of did it like in the other one. 2 out of what?
100.
So 2.0 watt, though. What unit would I put on that? Grams over 100 watt. Volume, so ml. See, mass over volume, so grams over. Okay, so let's take this 450 milliliters of solution, and it's times 2.0 grams. What's my solute? What is the solution of? Potassium. Huh? Hydroxide. Yes. So, so that tells you how many grams of potassium hydroxide you would have to use to make your solution. So, There you go. So if you wanted to make 450 milliliters of a 2% solution, you would take 9 grams of KOH and dissolve it up until you had 450 milliliters total. Okay. Okay. I'm going to skip this one. So, like I'm showing you here, we can write several different percentages different ways. So let's say I had the percentage 4.90 mm. What's mm? Mass. So grams per gram. So what's another way to think about 4.90%? Well, we know one way to write it is, that means there's 4.90 out of 100, right? 4.90 out of 100, right? That's what it's for percentage. And just like any kind of a factor like this, you could always flip it, say, it's 100 grams per 4.90 grams of NaCl. So depending on what you need to convert. So that's one way to think about it. Well, I could also relate it to just the solvent, because the solution is the sodium chloride plus the water, right? Right? So solution is the sodium chloride plus the water. Well, how much of that's just the water then?
95.1.
100's the total. Subtract out the 4.9, right? 95.1. So I could also think about it, there's 4.90 grams of NaCl just to 95.1 of the solvent. Or flip it, vice versa. So now I've related just the solute to the solvent. Well, I could also relate the solvent to the solution, like that. So that 1 percentage, I can get 6 different conversion factors out of that 1 percentage. I can compare solute and solution, solute and solvent, or solvent and solution. But they all come out of that one thing. There's 6 different ways to write that. Turn that into 6 different conversion factors. So the one you're most familiar with is this first one. 4.9 out of 100. The thing you're interested in over the total. But you could also say, maybe I want to know how much water do I have to add. So I'm going to focus on just the solvent. 4.9 out of 100 minus 4.9 gave me 95.1. Everybody see where this came from? Because this, right? Son of a gun. Because this right here, right? That is the 4.90 plus 95.1. That gave me the 100. Okay. So let's just try something here. Okay. What mass of a 5.00 mass percent solution of dextrose contains 25 grams of dextrose? So here you go. Here's like a little IV bag I had a picture of I found in the book there. There you go. So let's try this out. So 5.00 m/m percent? Well, that's the same as saying 5.00 grams of, what is the solution of? Dextrose. Over how many grams of solution?
100.
5 out of 100, yes. Not a trick question. All right, so that's what that means. So now I want to know what mass of solution, so I want grams of solution, contains 25.0 grams of dextrose. So I have 25.0 grams of dextrose. How can I use this percentage to get rid of grams of dextrose and find grams of solution?
Just flip them over.
Just flip it over, right? And put it as a conversion factor. So, 5.00 grams of dextrose and 100 grams of solution. That'll give me grams of solution, which is what I want. So there you go. So now you know. Oh. So it's like 500, right? Yeah. So there you go. So if you gave a patient 500 grams of solution, you're giving them 25 grams of dextrose. Or if the order was, hey, this patient needs to get 25 grams of dextrose, you would have to give them 500 grams of the solution. Are you with me? Okay. By the way, this 100 is an exact number because the percentage. Percentage is always out of 100 exactly. So that's not like one sig fig. 100's, yeah, exact, been defined. Percentage is always out of 100. Okay, we got 2 minutes. We're not going to have time to finish everything up, obviously. So let's just try one here together. What mass of solution contains 50.0 grams of phosphoric acid and a 6.50% mass solution? So I want to find mass of solution. I have this stuff, mass of solute, and the percentage of the whole solution. So 50.0 grams phosphoric acid. You don't know what that is yet, but I'll just tell you it's H3PO4. Or if you don't know, just write acid. It doesn't matter what it is. You just write acid if that makes you feel better. I'll just write acid. Let's just do that. I'll make you feel better. But I don't want grams of acid. I want grams of solution. Oh, well, that 6.50% tells me the ratio of acid to solution, right? And it tells me there's 6.50 grams of acid per every, what? 100 grams of solution. We punch that in, and what do you get? Anyone? Bueller? 7 what? 769? There you go. So if you needed to get 50 grams of phosphoric acid, you would need 769 grams of total solution to get that out. Okay, well, yes, we did not finish. I can figure out the schedule next semester. It give us 3 days for this. But, so we'll have to push the test back. But I'm going to warn you again, like I did in the last test, that does not mean wait until Monday to start doing the homework. And last time I saw, like literally half the people waited till Monday to start doing the homework. And they got crushed. So you have an extension. You have an extra 2 days. So today or tomorrow, work on this, practice it. The next day, the weekend, go to the tutorial center, whatever, right? So please do not wait till Monday. And as far as science fair people go, I will see you